Welcome to the lecture on modern digital communication techniques. We have started discussing about the different components of a digital communication system. We are also talked about little bit about the concept of layering and standardized interfaces. So we'll quickly review what we discussed in the previous class. We have looked at the source encoder. Roughly speaking, this is the source encoder in the previous lecture, and we have said at the last moment that well, this binary interface was pretty well defined in the previous lectures, and then we added the different interfaces that come in between these components, and these can be thought of as layers, different layers. And what we said is that these interfaces are very important. So the last thing that we also said in the previous lecture is that if I would take a view from this point, that means if I would see from here, when I am seeing from this side, I can think of as if this whole thing is a channel and symbols are going in, symbols are coming out. And what we discussed before is I can think the whole thing is a channel, binary symbols are going in, binary symbols are coming out. These are multi-amplitude symbols. And if we are here, because there is a sampler, these are discrete samples, so analog sequences. Why analog? Because it is just a sampler, so it can take a continuum of values, and this one quantizes these values. So that's the difference between this interface and this interface. It takes specific levels, and this one takes a whole continuum range of values. And this, because it's table lookup, it gives similar analog sequences, but of course is going to produce these quantized values. And this analog filter is going to recreate this waveform. So here again, if I look at it, this would appear like an analog sequence channel, this whole thing, taking in sequences, giving out sequences. So overall, this is the way we talk about standardized interfaces and layers. We'll continue this a little bit more and see some other important aspects of a digital communication system before we take a deep dive into each of the components in upcoming lectures. So continuing further, we can more or less say that the input and peer output of each layer encapsulates all lower layers Similarly, higher layers can be viewed in aggregate as simple source and destination. So like we are seeing the lower layers, any interface, like when we talk about input and peer output, the input and peer output, look at these two, they encapsulate all lower layers. That's what we have said. These inputs, they actually take care of these lower layers. We don't need to bother about it. Similarly, if you are viewing from this angle, if you are seeing from this side, what you can say is that as if this is the source, this is the destination. That's true for this. Now, if you are here in the middle, if I am here in the middle and I am looking from this side, you can simply say there is some source, which I don't know what kind of source it is, but it generates a sequence of symbols, and this is some destination which takes a sequence of symbols. That's it. So this whole thing becomes a source, this whole thing becomes a destination. Similarly, if I put my boundary point here, I would say that it is some source which produces binary signal, it is some destination which takes binary. So I can compare this input to output and say what kind of channel is this, how much percentage of error is there. Similarly, I can compare here and say what kind of distortion has come in. Here again, since these are symbols, I can talk of symbols going into here, error, I can talk about sequences, the signal to noise ratio, or the distortion, the total amount of distortion here. I can talk about bits in errors and so on and so forth. So that is what is summarized in this particular statement, that the input and pure output of each layer encapsulates all lower layers, as we've just discussed. Similarly, the higher layers can be viewed as aggregate of simple source and destination. So what this is telling you is to partition the big complex communication system into interfaces through which I can encapsulate everything on the left and say let that be the source if it is the transmitter, and if it's the receiver I can say that is the destination. If I look it on the other side, I would say that's the input to the channel and that's the output from the channel, and so on and so forth. So if we move forward with this description, now let's take a look at a brief overview of the different components of a communication system. I have another different picture to share with you. In general, of course, we can talk about communication systems, this layering. A general picture is of course there. Let me just quickly draw the general picture so that we complete it. This is module I, this is the input, this is the interface, this is input module I minus 1, this is a very generic picture, and there is an interface, and so on. It continues. This is the output module, and this is the interface from I minus 2 to I minus 1. Look at this. This is the I minus 2, this is the I minus 1, and this is from I minus 1 to I, because this is I. Output module I, and this is of course the input, this is of course the output. So this is the interface of I to I minus 1, I to I minus 1, I minus 1 to I minus 2. This side it is I minus 2 to I minus 1, right. So these are all input modules, and goes on to the last module, input module 1, goes into the channel. This is output module 1, and so on and so forth . So this completes the picture and this definition along with it. Now with this, since we have been talking about the source, the point to point source, so we will continue and briefly tell you about the other part. So whenever we have a communication system, what we have just described is a point source and a point destination. But as you are aware that, and we have also mentioned in the beginning, we are talking about the big networks. So the study is divided into the core network, which is all network theories, and also point to point links, which is basically what we are going to consider over here. And when we talk about point to point links, since there are various parts of the chain, things are in so great details that there is a specialization for antenna design, specialization for RF circuits, there are specializations for VLSI integration, for analog to digital even conversions. So what we are going to look at is that part which where we generate bits, from bits right to the point where we are generating samples which go into the analog to digital converter, and back at the receiver from the point where the signals get converted to digital, and inside till it gets converted to bits. So this is the broad or main section where we will be putting our efforts and focus in this particular course. We will not look at much into networks, because that requires development of a whole set of theory, which is not this particular course. So with that brief disclaimer, you can say we can still talk about a few pictures about the network and how to encapsulate them in a similar way. So if we take the network aspect, probably only once, that's it, just to complete the story. The network aspect in a similar way, we have the source input. That's what we have been doing. The source input goes into the source encoder, whose block diagram we have discussed, and we will go into each details of the source encoder blocks later on. Then we can say that the source encoder output goes in to the TCP input. By TCP input, what we mean is the transmission control protocol, or the TCP protocol, which you generally use for the TCP IP address setting, or which one you use for quality of service, error corrections, and so on and so forth. So this is going into the network layer. There also we can put this interfaces and layering, and probably people in that particular arena are more often encounter the word of layering and interfaces than the digital communications, but it spans over the entire region. So from the TCP again, you have an interface to the internet protocol, which is again the input. Then again you have the data link controller input, and finally going to the channel encoder, right. So when we had written channel encoder, we did not mean these things, but again these could become part of channel encoder in our earlier diagram, but this is generally what it happens. From the channel encoder, which generates waveforms, it goes to the channel, and the reverse procedure we will see some of the components. This is the IP output, this is the TCP output, goes finally to the source decoder. Of course, you can have several components in between this also, which is the presentation layer, and so on and so forth, right. So this is also applies to the network layers or the TCP layers, the way of layering and interfaces, and the interfaces here in these points are more or less much clearly defined than the interfaces that we have been talking about in our earlier discussions. Okay. So moving on further, when we talk about, now let's go into and talk about the different components of the transmitter and the receiver or the channel that we have, and talk about briefly about their attributes, which can help us in getting a broad overview of the systems that we are going to encounter. So if we talk about the communication sources, they can be discrete in nature, which we all know, and it can produce a sequence of discrete symbols, and example of them could be letters of alphabet, could be any language, could be English, could be Bengali, could be Hindi, could be Chinese, and so on and so forth. That means they are discrete, they are specific symbols, and they have a whole set or a group from which they are selected. These are kind of discrete sources, and you also have analog sources. So when you have analog sources, they are analog waveforms, of course. Example, speech, voice, you can say voice, video, image, photograph, and so on and so forth. Of course, they can be digitized. That's what we have said. You can always digitize them, but primarily they are analog sources. A picture is an analog source, the original one. But then, of course, the way you capture it could be, it becomes a digital thing. Okay, and now if you look at this, what we have with us is the source will be modeled as a sample function of a random process. This is important to know, because if it is analog, well, what kind of waveform is going to come, we don't know. If it's image, what kind of image, we don't know. So that's random, of course. If we are talking about discrete sources, let's say a passage or an essay which is going, or a note or a lecture or something which is going to get transmitted, we don't know beforehand what particular sequence is going to go through, although we know that they are from the English alphabet, but we do not know that what specific letters or what specific words are going to get formed in this particular transmission. So we can model it as a sample function of a random process. So this is something important which we should keep in mind at this stage. This particular thing could be making sense here when we talk about this analog process, but it is not quite obvious when that things would be treated as a random, because if you look at the way earlier communication systems were designed, they used to take a communication system and think of it as carrying sinusoids, exponentials. So you could also think of a speech or a video or any particular signal. If I say that we have a particular signal, let's say I have this signal. What comes to your mind is through Fourier analysis you can break it down, and you can find the components of frequencies which build this signal. So there will be, let's say, a whole set of sinusoids, a huge number depending upon the bandwidth you restrict your system, and you find a coefficient for each sinusoid. So when you add them up with appropriate phase and amplitude, you can regenerate this particular signal. So what they studied initially is that what is the response of a system to a particular sequence of or to a particular set of communication or sinusoids. So you would excite it by sinusoids, you will get the signal. And if you look at very early communication systems or telecommunication systems, what they did is they carried these original voice messages across miles and miles, tens and hundreds of miles across, and they just simply carried the signal across through this whole entire region. Now then there was a change of view at a certain point of time. What was realized is that, well, if this signal is made up of several sinusoids, means let's say I call it ak e to the power of j omega k. If I say I can recreate it, k equals to, let's say, 1 to, actually it goes to infinity, but still let's say we have a finite number. Okay, k is the index, so that's why I'm taking it only positive. So it could be, the values could be anything. So if we have that, then we could say that, well, if I can break it down into these frequency components and I can again regenerate it by using appropriate coefficients which has amplitude and a phase factor, then what is the need to actually carry this whole signal across? What's the need to carry? You probably don't need to carry it. You can simply regenerate it. You can simply regenerate it at the receiver. Now to regenerate it at the receiver, what do you need? What you need is basically these coefficients which capture both amplitude as well as phase. So you have to predefine that at the receiver it knows the set of frequencies which are going to be used. So if there is a certain amount of bandwidth, let's say, present in the system, you say that, well, I'm going to use 20 or let's say 100 different frequency components. Of course, there will be distortion, there will be some kind of error, there will be some kind of problem, but if it is acceptable, then you would fix to a certain number that so many components of frequencies I'm going to use to regenerate my original voice message. If it is true, then what you need to do is send these coefficients across. If you can send these coefficients across, then at this point it can generate. So again, what it turns out is that you are choosing a certain set of coefficients for a certain set of sinusoids to be transmitted, and they get regenerated at the receiver. Again, you can break down the problem further and you can analyze it, or you can think of it that end of the day what you are doing is sending sinusoids. That means the receiver knows that I am dealing with sinusoids. If it's English, then the receiver knows that it has to choose from the set of letters that is present in it, right? So what we are trying to stress over here is that this particular waveform or the particular word that is going to be transmitted is not important. rather the choice which is important. This is quite different from the earlier view. When we mean choice, what we say is that suppose I know that there are ones and zeros. The receiver also knows there are ones and zeros. So basically the transmitter and receiver should know the language they are talking. That is very, very essential, and that's always true, because even if you think of communication, when we talk to another person, we use the same language. So we are talking about the language of communication, we are talking about the syntax or the grammar of communication. The same things apply over here. So they know what language they are talking about, and they also have to agree upon what is the syntax or the protocol or the method of communication. So once that is established, then communication would mean that the transmitter is going to send to the receiver that at this point whether it has a 1 to send or whether it has a 0 to send. This is not known a priori. What is known a priori at the receiver is a 1 will come or a 0 will come or nothing else will come. You are not going to get a, you are not going to get a b, you are not going to get a sinusoid, but you are going to get these two in this particular case. If we are talking about transmission of English letters, the transmitter knows that it has to send these letters. The receiver knows what it's going to receive are only letters of the English alphabet and nothing else. But the receiver doesn't know which particular letter of that alphabet is going to come. In this particular example that we are drawing over here, in this particular example, the receiver does not know at this instant of time whether a 1 is going to come or a 0 is going to come. So what we are trying to convey to you at this point is what is important is that there is a choice which is actually going across from the transmitter to the receiver and nothing else. It's not actually this 0 or this 1. This could be represented in any way. These English letters could be represented in any way. The picture, the image could be represented in any way. What is important is the choice. Now once we are assured that we are talking about a choice, then things become a bit different. So we can summarize what we said, and this is primarily due to Shannon. That is where we are talking about information theory. So primarily due to Shannon, his view was that if the receiver or if the recipient knows that, we can summarize what we have written, that a sine wave of a given frequency is to be communicated, then why not regenerate it at the output, right? This is one of the views that we have stated. The second thing that we are going to state is that if the recipient knows, knows a sine wave and nothing else is going to come, if it knows that the sine wave is going to come of an unknown frequency, then what does the transmitter need to do? The transmitter needs to send the value of the frequency. That's it. If it sends the value of the frequency, this is taken by the receiver regenerates, right? This is the primary idea from which it expanded or it got abstracted to the point where we are talking about the choice. So if it is a continuum, it's a little bit difficult problem, but if it is a discrete, or if you can break it down into discrete, and that's what we said in the earlier lectures, that if at all you can communicate, you can communicate in a binary mode. So that means you are able to bring it down into binary. So if you're going down to binary, finally you have a choice between 0 and 1. So if you have a choice between 0 and 1, what is important is not the 0 or the 1, but the choice between 0 and 1. That's what is getting communicated from the transmitter to the receiver. Now here this is very, very important. So again, according to Shannon, what we would write is the set of possible source output rather than any particular output is of primary interest, because the reason is that the communication system must be designed to communicate whichever of the possible source output actually occurs, and then we can write the objective of the communication system is to transform each possible source symbol. This is what we have stated earlier, but we are refining it. Source symbol into a transmitted signal in such a way that it can be distinguished at the channel output, and hence a probability measure is needed. I would rather place it like this. A probability measure is needed on this set of possible source output to distinguish the typical from the atypical. Now, this might be a bit cryptic, so let us go through it, and this will finally converge to what we have already said. So, what we are saying over here is the reason for this, that what is important is the choice rather than the particular output, is that communication systems must be designed to communicate whichever of the possible source output actually occurs. This is clear because we know that zeros and ones are going to come. So, the 1 or the 0 is not important, but which of the two is the choice, basically that is important. So, the communication system must be designed to communicate whichever of the possible source output actually occurs, and the objective of the communication system is to transform each possible source symbol, that means the 0 or the 1, into a particular waveform. That is what we have said earlier, but now we are refining it in a little bit better way, that the transmitted signal can be distinguished at the channel output. This is important. Earlier we said reliable. So, this is the part of wave shaping. So, suppose I send a sequence of zeros and ones. The way you should design the communication system, all it is trying to say is that the 1 when it is sent and received and 0 when it is sent and received should be distinguishable. So, the very simple example is if I am talking about sending a 1 using this waveform and sending a 0 using this waveform, right. I should be able to distinguish based on the frequency. If I am using this as 1, I could use this as 0, distinguishing it by the amplitude. Then we could also use the phase information, but the way we should do it is that we should be able to distinguish. If we are not able to distinguish, that means we are going into error, and hence it said at the last point that a probability measure is needed on this set of possible source output. Now, what it tells is that if I have a source, that means let us say which is generating English letters, let us say a human source, let us say, which is speaking, it is generating some textual matter. In that case, if you plot the histogram of the words, or if you plot the histogram of the letters, then what you finally land up into is a probability measure on the letters. So, basically you can say each symbol has a certain probability of occurrence. What will come clear, how does that help us in designing the first component of a communication system, which we are going to see in the next lecture. Thank you.